Can,
Okay. You see my iPad screen there,
yes, I can see.
Basics.
and you see my scribble.
Yes.
Yeah.
Great. Okay. Um, well, thanks for having me. It's a pleasure to come and speak to you today. Um, and let's see, let me pull up the chat. So I've got the chat here. If you want to jump in with any questions in the chat while I'm speaking, I'll try to keep an eye on it, but also feel free to interrupt. And I will do my best to tell you some things succinct and on time. I guess I have 45 minutes. Um, so we'll see how far I get into the story. The uh, the basic question is, really trying to understand this idea of EFT geometry. And so I want to spend most of my time uh, today basically just kind of setting up the question, what does EFT have to do with geometry? And what is the puzzle that we've been trying to solve? And why is this non-trivial? And then at the very end, if I don't terribly run out of time, I'll say a few words about our proposal for how to think about this in a broader context. But for now, I just want to start with a primer on what's called field space geometry. And which is the kind of standard notion of EFT geometry. It really goes back all the way to this fantastic paper by Volkov from the 1970s. Okay. So the basic idea here is that we start with the following toy model for EFT, which is we have real scalar fields, phi I, and we write the Lagrangian, uh, 1/2 g ij of phi minus d mu phi I d mu phi j. So this is, in particular, this has no potential, just for simplicity, and it's truncated at order d squared, okay? Which again is done for simplicity, but as you'll see, understanding how to generalize for higher derivatives is a part of the places where there's new developments. And so, in this idea of no potential is again just a simplifying assumption here. Incorporating the potential is straightforward. It's well known how to do that. Um, and this is some function of the scalar field's a generic function. Okay, so you should think about this as a derivative expansion where we could have any power of the fields here. And again, so that's kind of a toy model of EFT. And in particular, this is a way of writing the leading terms in the nonlinear sigma model. Okay. So the key idea is we know that physical predictions are invariant under field redefinitions. And in fact, just to advertise a little bit of my own work, uh, recently I revisited this question with Andreas Helset and Matthew Forslund. We have this fun paper that's now about a year old, where we realized that actually the space of allowed field redefinitions is a bit broader than people in the EFT community had appreciated before. But also in this paper, if you don't know this, I know we have some young people in the audience here. So if you don't know this fact, then we give a really nice, what I think is a really nice diagrammatic proof in this paper. Okay, so that's something to check out if you're interested. So the idea of EFT geometry is to take this fact that's kind of a textbook fact about, say, S matrix elements and make it manifest. And the key is that if we go back to this Lagrangian here, let me maybe do some quick iPad magic. Okay, so we have this Lagrangian. Well, then this coefficient here has the following three properties. So it's symmetric, Gij equals Gji. That's obvious because the kinetic term is symmetric under the exchange of I and j, so this has to be true. Then the second fact is that Gij inverse exists. That's because we're assuming that these are scalar fields in a quantum field theory, and that means that they need to have a non-trivial kinetic term. So this thing is going to have ones, at least when it's canonically normalized, along the diagonal plus functions of the field, right? So this thing is proportional to the identity plus order phi, and that means that its determinant is non-zero, so the inverse exists. And then the third thing is that under a field redefinition, Gij goes to G tilde KL as a function of phi tilde, which equals d phi I, d phi tilde K, d phi J, d phi tilde L, Gij function of phi tilde. Okay, and that's the minus sign. Yeah, so maybe I have the sign. I thought I had the sign right because I had it wrong before. But the minus sign is there so that the leading term here is proportional to 1. So let me think about it for a second. So if I have um, mm, mm, let's see, I integrate by parts, and then I have, yeah, maybe this is a plus. This, I may still have, this may be an old, oh, you know what? This is an old version of my notes. Yeah, this is a plus, indeed. So the idea, right, I'm assuming the mostly plus metric, okay? And then this is supposed to be something that looks like, this looks like 1 plus some function of the fields. Great, thanks for that. Yep. Very good. So the this equation is simply a consequence and ask me if it's too fast, but hopefully it's straightforward. You can see that when I plug in some field redefinition in these derivative terms, right, I'm going to generate derivatives, right? And so I can make this identification, and the Lagrangian is unchanged. And I interpret this. This is just the transformation property that tells me this is a two tensor, right? Um, and so the when I have something which satisfies these properties under um, that it's symmetric, invertible, and transforms as a two tensor, that tells me that this is a candidate for a metric. And so the basic idea then is to interpret this coefficient here, which is generating interactions for us, as some kind of metric. Okay. So then the question is, what good is that? Well, it turns out, let's just introduce kind of a standard definition. So let's define the amputated correlation functions. Okay, so this, I'll call them A, and I'll give them indices I, J, N, and these are just the limit as P I squared goes to M I squared um, times some wave function factors. Okay, so here this bar means evaluate at the vacuum. Okay, so impose the equations of motion, or in other words, phi equals phi bar is equivalent to taking the external currents to zero, okay, in the path integral. Um, and these, I'm using e's instead of the z, which you may be more familiar with, just for, it's just a notational uh, convenience for that we used in the paper. But these are just the wave function factors, right, which take us from a field index to a particle index. Okay. And so the so these are the standard amplitudes, and these objects are the amputated correlation functions, which we can define off shell. Okay, so M can be defined off shell, and for a generic uh, and for J not equal to zero. Okay, so now um, with these definitions in mind, if we just take this theory, this one here, and we compute these amputated correlation functions, then what we find is Mij, the 3-point is 0. Mijkl takes the following form, Sij Rij, sorry, Ri, oh, the details are not so important, Ikjl plus Sikrijkl, okay? And the 5-point, Ijklm, is something of this form. That's an R. Riklm plus other terms that look like this, okay? And in particular, we see that this object R and this object, which is the covariant derivative of R, appear where this is the Riemann curvature tensor defined in field space, and this is the covariant derivative defined in field space using the metric uh, defined here. Okay? So this is really nice because, for one thing, these are beautiful compact formulas for objects that we care about in quantum field theory, which are written in this generic way. So given a theory, right, I specify G, Ij, and then I can immediately turn the crank on my GR formulas and get out the Riemann curvature tensor and the covariant derivative of the Riemann curvature tensor and immediately compute these amputated correlation functions. And the other thing that this does is it makes the uh, covariance properties of the underlying invariant quantity more manifest. Okay. And there's been lots of applications, some by myself and collaborators, and by many groups looking at applying this formalism to various questions of both kind of phenomenological and theoretical interest. Okay, so just to list, if you're interested, a few applications. For the pheno-oriented among you, I think the most important modern application of this is this question of the standard model effective theory. So there's the more general Higgs effective theory, which is kind of the nonlinear sigma model version of the standard model is an effective theory where we think about, where we write down all possible terms that are consistent with the nonlinearly realized SU2 cross U1 of the electroweak sector versus the SMEFT, which is the standard way we formulate and write all possible terms consistent with SU2 cross U1 linearly realized. There's also a very nice result from Chung Halstead and Parra Martinez, which is the so-called geometric soft theorems, which is a beautiful result showing that the idea of the Adler zero, which is one of the classic aspects of the nonlinear sigma model, can be generalized to a broader class of theories using this geometric language. So this is very nice. People have done loops and renormalization group evolution. So this is not just a tree level accident, but actually something that persists at loop level. Okay. But in all of these cases, we're always restricting to essentially to this toy model of EFT, plus a potential. Okay. And something I haven't emphasized yet, but that's critical, is that this derivation here, okay, is assuming field redefinitions without derivatives. Okay, so this covers a wide class of field redefinitions, but it doesn't accommodate field redefinitions that include derivatives, which of course are allowed. And that's kind of easy to see from this structure, because here, right, we see that if we did a derivative field redefinition, we would mess up the derivative structure here. We would mix this term with higher order terms we're not writing. Okay, so it's kind of obvious from the way we wrote it here that we can't do field redefinitions with derivatives, but also you can kind of see it here in these formulas. Okay, we see a factorization of the momentum dependence in terms of the generalized Mandelstam variables and the field dependence in terms of the Riemann curvature tensor. And so again, if you did a field redefinition without derivatives, this factorized structure is maintained by such a field redefinition. But if you do a field redefinition with derivatives, then it's going to mix sort of, if you like, you can think of it in a generalized sense as mixing this field indices with these momentum indices. Okay? So what we want to do is we want to understand if we can generalize to along the way we need to understand covariance. So I've alluded to the sense in which these objects I was writing are covariant, but it's more subtle than just generic covariance. We want to discuss higher derivatives. Okay. I can't spell just use the variable higher derivatives. Okay. And we want to generalize to derivative field redefinitions. Okay. So that means we need some kind of bigger framework. And this is something we've been thinking about for a long time and that we have been calling functional geometry. Okay. Great. So before I move on, happy to pause and take more questions because this is kind of the main setup.
Can I ask you, just to be sure, where you write this 4-point, 5-point, do you contract indices, or because it seems to me that indices somehow don't match if you contract them?
Yeah, thanks. The way I wrote the way I wrote this is kind of confusing, but yeah, these are not contracted, as you say.
Mm.
So often if you look in the literature, you'll see that this will be written with kind of IJKL indices. This will be written with 1 and 2 indices, just to make that more
Mm,
clear. Uh,
I
but
see.
but yeah, indeed, this is kind of a separate. So the kinematics associated with this leg and this leg are the kinematics that appear here. But yeah, there's no summation, as you say, because then ultimately, right, we want to when we want to compute an S matrix element, we want to contract this with these factors, right?
Mm-hmm.
And take the on-shell limit.
Okay, thanks.
Yeah, thanks for the question. That wasn't clear. Um,
Oh, well,
great.
can I ask a question
Yes,
about
please.
higher derivative?
About what?
Oh, higher derivative. So,
Um,
well, yeah, I mean, so usually they have ghost, the Oster-Gradusky ghost, and so yeah, I want to know. So, is there any anomaly to calculate amplitude like this one with higher derivatives?
Good. So I'm not thinking about higher derivatives in that context. Here I'm thinking about higher derivatives just purely in the sense of an EFT expansion, right? So there are no ghosts because this is all taken as a low energy expansion where I quantize the theory as though it's free theory, and then I add the higher derivative terms as interactions, and they don't change the number of degrees of freedom. So this
Oh,
is this is
okay.
yeah, this has
Well,
nothing to
I
do with
mean,
gravity, right? This is doing quantum field theory in flat space. All of the curvature we're talking about here is curvature in field space, which is just a way of uh, accommodating and packaging the interactions in the EFT. Okay.
oh, okay. I meant, well, how should I say? Well, so yeah, of course. So EFT expansion is well defined, but so just I'm curious about what happened um if it has a higher derivatives because so usually they have anomalous behavior. Uh, I'm not sure at amplitude. So maybe so the propagator will have a different sign uh, because of the higher derivative cost. So
No, but this is exactly what, yeah. So indeed, you can have, I mean, people study theories where they try to incorporate higher derivative terms into, say, a definition of the propagator, and then try to compensate that with some ghosts, as you say. Here, we're taking the much more sort of classic and mundane attitude that this is just an EFT at low energies. It just looks like standard particle physics where the higher derivative terms just give us higher derivative interactions, and there's no new anomalies, there's no subtleties like that, right? So we're really just doing a low energy expansion. Of course, because we're doing effective field theory, this theory is not UV complete, right? It breaks down at some scale. I'm not specifying that explicitly, but that's, kind of built into the form here, right? This is going to have some scales when I write the higher derivative expansion. This is also, sorry, the higher field expansion. This is also, in principle, has an arbitrary number of fields in it. So there's going to be some, non-renormalizable terms that are going to cause, say, partial wave unitarity violation at high energies. But that's all okay because we know this UV completes into some deeper theory, right?
yeah. Thank you.
Okay. Yeah, we're not addressing any kind of trickier field theory questions. We're really just trying to understand applications to the standard stuff. Right. Great. Okay. So let's see. In my last uh, um, I stop at 1:30, right? So I have about 20 minutes. Um, so the let me just tell you a little bit about what a generalized framework needs to look like, okay? Oh, sorry, I see a question here. Complex scalar fields. Yeah, everything everything follows if you use complex scalar fields, indeed. And in fact, I should have mentioned, actually, there's one of the sort of frontiers of this is understanding theories with fermions. So there's a sort of version of something that looks like superspace where you can geometrize EFTs that involve fermions. That story is not complete. There's still some open kind of technical issues, but at least conceptually, there's been a lot of progress in understanding that. Gauge bosons, there's very little understood because with gauge bosons, there's this kind of obvious issue, which is that field redefinitions and gauge transformations are one and the same, right? So somehow a geometric picture that involves gauge bosons is also going to have to know about gauge invariance. And so that's something where there's not really much work done. That's kind of an open frontier, even when you're just studying kind of the simpler theories with only two derivative terms. But certainly when it comes to complex scalar fields, applications to the real standard model, there's no obstructions at all. And of course, as you know, you can write a complex scalar field just as real scalar fields. So even everything I'm saying, you can kind of frame your theory with complex scalar fields in this language if you want. Great. Okay, so the first thing I want to discuss, and maybe I'll keep it pretty conceptual. I won't write too many of the formulas because I don't have very much time. Is that when we look at these formulas, and many people over the years have stared at these formulas, the naive thing you would assume, because this has these open indices in field space, is that this object just transforms covariantly. Okay, but actually that is not quite the case. Something that we realized a couple of years ago and kind of worked out in a series of papers is that these M's have a notion of what we call on-shell covariance. Okay, which is it didn't have to be the case. It could be the case. It could have been that these stripped amplitudes, off-shell amplitudes, would be manifestly covariant. And again, when you compute these formulas, you see this form, and you would be led to guess. And in fact, we assumed that that was the case. And then we started checking, and we found that no, in fact, there was a broader notion of covariance, which is that when we transform our matrix elements, what we find, these off-shell stripped amplitudes, right? These off-shell matrix elements, if I do a field redefinition and I get some m tilde with indices 1 through n of phi tilde, I get something of the following form. So it has this tensor transformation structure, that's a D, D phi tilde n, times m. So now here I'm just using upper and lower case for the indices before and after the transformation, okay? And that's phi tilde. Okay, plus, so that's the covariant transformation, and then plus some quantity I'll call x of phi tilde, where x has the property that when I take the limit, p squared goes to m squared, and I multiply it by these wave function factors, and I take this bar operation, right? I take the vacuum, I set the j's to 0. This quantity vanishes, okay? So we abbreviate this. If you look at our most recent paper, which by the way, it should have said, so this is all, I think, nicely summarized in the recent paper, which I should have cited at the beginning. Okay, which I don't see in these notes. How funny. Okay, so I didn't include them, the citation in these notes, but it's a recent paper from me, and Zhusheng Liu, sorry, Zhusheng, that's my other collaborator, Zhusheng Li, and Kevin Zhang, from just a few months ago, and so 2005, 25. So in this paper, we really try to articulate all this stuff very clearly and really try to build everything from the ground up. So if I get you interested in this subject, which I hope this talk will inspire you, then I definitely suggest taking a look at this paper, where we kind of try to be comprehensive about all these issues and tell the story from the start. Okay, so in that paper, we introduced this notation, which just means that there are these extra terms that show up in the transformation when you just take a field redefinition and plow through and do the new computation. What you find is you indeed find a tensor-like structure, but you also find this other stuff that only vanishes on shell. Okay, so it didn't have to be like that, but at a minimum, this had to be true, right? Because we know for sure that the on-shell amplitudes are themselves invariant. So in some sense, this object had to have, this is the most general type of transformation that this object could have. But nonetheless, it's pretty straightforward to see that this is what happens, is that you generate this unfortunate non-geometric stuff. Okay, so this tells us immediately that there must be some broader notion of covariance. So the building blocks of geometric amplitudes should have on-shell covariant. And in fact, the progress that we made in this recent paper is that we've now identified what I believe are the primitive on-shell covariant building blocks that you can use to make everything manifestly on-shell covariant at every step of a calculation. So let me just give you an example, okay, of on-shell covariance. So, for example, if I have a potential, let's call it U, okay, because I'll use V for vertices if I get there. So if I have the potential U, then the first derivative of the potential has to be on-shell equivalent to 0, right? Because we evaluate the theory at the vacuum. That means we're at the minimum of the potential. Notice that here, I'm using the standard GR notation, right? Where I'm using comma for a regular derivative with respect to some quantity, right? So here I'm taking the regular derivative with respect to the field with J index, okay? So this is sort of true. This has to be true, right, by definition. We can also look at the inverse propagator. Okay, so the inverse propagator takes the following form. So we'll call it delta tilde inverse ij of p, and that's d phi k, d phi tilde I, d phi. This is after doing a field redefinition, sorry. Delta k L inverse of p, right? So I have the inverse propagator, but then there's this other term, d squared phi k over d phi tilde I, d phi tilde j, u sub comma k, okay? And so when I do a field redefinition in the 2-point function, or the inverse propagator, okay, I get a tensor-like transformation here, but I also generate this thing. But notice this is proportional to the derivative of the potential. So because the derivative of the potential is 0 on shell, this term is on shell equivalent to 0, okay? So we see that the inverse propagator is what we call on shell equivalent to a 2 tensor, okay? So this is the basic idea, is we want to define quantities like this one. So let me just write this as a formula. So this is on shell equivalent to an object. I'm going to give this double line, right? Like bold, where I can define this thing as Gij p squared minus u covariant derivative with respect to ij, okay? Where, again, I'm using the GR notation. This is now a covariant derivative, right? Where this means u comma ij minus gamma ij k u comma k, right? The covariant derivative, where this is just the standard Christoffel symbol, okay? So the point is that the propagator is already on-shell equivalent to something that's manifestly geometric. Okay, so the game is to look for manifestly geometric vertices. So let me skip to the punchline, which is the main claim of our paper, okay? Which is that, so here's the claim, which if I had another hour, I would tell you about, but here I'm just going to advertise. The main claim is that mi through n as a function of pi p n is some function I through n of propagators and vertices v. Okay, this is the Feynman diagram expansion. Okay, not at all obviously geometric. In fact, those formulas that I wrote a little while ago, which had that geometric property, it's quite a bit of work to get it into that geometric form. Okay, so it's I encourage you to try to sit and work out the 2-point function, the 4-point function, and especially the 5-point. It's quite non-trivial. Okay, it's a couple of pages of intermediate algebra in order to get it into that nice form. So we claim that this is equal to the same function of the deltas and now something I'll call curly v, okay, where these curly v are a new object. These are on-shell covariant vertices, okay? So we claim that even in the standard notion of geometry and field space, that the way to see geometry manifest at every step is to do something very much like the Feynman diagram expansion, but to use a different set of vertices than the naive ones you would get out of Feynman diagrams. And in the paper, we provide concrete formulas. Everything's extremely explicit. So there's just a set of formulas to go from here to here. Okay? Good. So I'm running out of time. I'm going to tell you one more idea, but before I do, I'll pause and see if you have any questions about this. Okay, keep thinking because I'm going to tell you one more thing, and then I'll be happy to take any questions at the end. Okay, so I'll try to wrap up in 5 minutes. Okay, so everything, like I said, this is all based on, observations from the 70s even, that started way back in the 70s, and there's been a lot of literature on this stuff. especially in the past decade. And so you might ask, uh, what's new, given that why bother reformulating everything when we already know we have these nice results? Well, the answer is that it has so far not been obvious how to go from the vertices and Feynman rules in this toy theory with only two derivatives to the more general theory where we accommodate field redefinitions that involve derivatives. And what this reframing of the question in terms of these on-shell covariant vertices does is it makes the uplift to the more general notion of geometry and field space completely manifest. Okay, so now I'm going to write formulas that look almost identical to what I just wrote. Okay, but the notation is doing a lot of heavy lifting, and so I'll just quickly highlight that notation, and then I'll close and take any questions you might have. And if you're interested in the details, of course, the paper is out, so you can look there. Good. So here is the upgrade to functional geometry. And let me also say, the way, of course, in hindsight, everything tends to be obvious. But I've been working on this question for about 5 years, and I would say if you had asked me like 2 years ago, I would have told you that this didn't exist. So to me, it's really been transformative and kind of a breakthrough for me personally that we have been able to show, at least at tree level, that there is an upgrade of geometry to functional geometry. Okay. So again, I'm going to write it in a way that kind of looks obvious, but I just want to emphasize that at least for me, none of this was obvious at all. And in fact, we tried and failed many times to figure out how to do this. So if you look in my papers, you'll see half attempts to define something like functional geometry that are not finished because they ultimately didn't work. We were optimistic at intermediate points, but then we realized fatal flaws. Okay. Whereas this, I think, we can see how it goes from start to finish. So I really think this is an answer to the question, what is functional geometry? Not claiming it's the unique answer. Okay, so here is the key formula. Notice it looks very much like the one I just wrote. Okay, but check out the difference. Okay, I'm just doing some clever tricks of notation. So now, if I go back here, okay, notice I use parentheses. And if you look in the paper, actually, we're more careful and we write momenta explicitly. Okay. Whereas here, now I'm using the square brackets because this is a functional of phi, not just a function of phi. And these indices are doing a lot more than just tracking the field index. They're also tracking the momentum. Okay. So one of the things is that a derivative field redefinition mixes the field labels and the momentum labels. So you need these indices to be an upgraded notion of a field index. It also needs to keep track of the momentum. And in fact, everything that we do in the paper is defined explicitly a momentum space to make that manifest. Okay. So this formula looks almost identical to the one I just flashed back to, but the interpretation is quite different. Okay. This is a functional of phi now, and these are both field and momentum indices together. Okay. So then our main formula is in this language. So M1 through N is some function 1 through N of the delta and some vertices. This is an M. Okay, so some collection of momented vertices. And this is equal to the same function. Again, the first thing is the thing you would do with Feynman rules. This has, again, an upgraded notion of indices that are now manifestly on-shell covariant. Um, and so these V are on-shell covariant for field redefinitions with derivatives. Okay. The previous formula I wrote, that wasn't true, but in this formula now, again, there's these indices are tracking both field and momentum. Okay. And we have explicit formulas for how to derive these V's, which are manifestly on-shell covariant. Okay. Um, and so this allows us to define a notion of functional geometry. Okay. Very good. So I've already am over time. So let me just end. So functional geometry exists. Okay. This is one of those statements that I would, I bet my house, maybe not my life, but I'm really quite confident now that this is true. I was skeptical. Like I said, I actually would have bet against it a couple of years ago. So to me, this is real progress. Um, and so there's lots of open questions. Okay. First of all, we need to put it to work. So we want to do things like generalize this EFT classification and Heft-Smeft. We want to understand universal formulas for the amplitudes for RGs. There's a big open question of loops. Okay, everything that I'm telling you, we proved at tree level, but of course now we want to extend this to loops. There's how do we accommodate fermions and gauge bosons. Um, there's um, there's also questions of defining a metric. Okay, so I didn't get into that. That's really a whole talk kind of in and of itself. Um, and so I encourage you, if you're interested, to take a look at the paper, or actually, if you're curious, I have kind of a set of summarized notes that I've been lecturing from that I'd be happy to share with you. So you feel free to send me an email uh, if you want to see the rest of the talk, at least the notes for the rest of the talk. This is one of my email addresses. So more than happy to share. So you can kind of get a summary, and then if you're interested, you could take a look at the paper. Okay, so sorry for going a little bit over time. I'll stop there, and I'm happy to take questions if there's time for it. Otherwise, again, feel free to ping me here if you have any questions or want to see notes on the rest of the talk. Thanks a lot.
Any question from the audience? Please unmute yourself and ask.
Well, if I can ask, but maybe I can see it in your notes, would be good to see a simple example, no, of this final part, how this curly V look like in a specific example. But probably I can check it in your paper.
Yeah, I mean, even one thing I can let me give you a half answer just because we're short on time and I don't want to take time from the next speaker. But let me give you some on-shell equivalence formulas, just a couple of the ones that are most important. Okay, so we have that the propagator is on-shell equivalent to this bold propagator, where this thing inverse AB equals S covariant derivative with respect to AB symmetrized. Okay. And then these V's are, again, the formulas are non-trivial that are in the paper. But what we show is that these are on-shell equivalent at tree level to the symmetrized covariant derivative of the action. Okay. So this really makes the kind of the covariance of this object manifest, right, up to these X factors. So this is really one of the kind of key things that it kind of needed to be true at tree level, but that we show explicitly that we prove this fact. One thing I'll just mention is that in our previous attempts to define functional geometry, one of the questions we had was how to map from functional geometry back to the sort of standard field space geometry. And one of the issues is that field space geometry formulas are kind of naturally expressed in the symmetrized form. And so something that was kind of a technical hurdle, but that we finally were able to figure out, it was how to formulate everything in this language where the indices were symmetrized, and that really went a long way towards helping us understand how to do this map. Yeah, I don't know, by the way, if on the Indigo page I can post. The organizers maybe could message me if I can just also post my notes, which I'd be happy to do. Post them on the Indigo page so everybody would have them. But if not, like I said, feel free to email me and I can send you these details. And the paper is online also, so you can take a look at the paper.
Yeah, thanks a lot.
Yeah, thank
Maybe
you.
very briefly, whether the scalar's massive or massless, so this changes something, or
Excellent. Yeah. So this works for massive and massless scalars. And actually, that was again something that's not so trivial to accommodate. The case with massive scalars. There's a close relationship between this and what's called the geometry kinematics duality. But this is for massless. And so another thing that we found a tremendous inspiration from this work. I think this is a fantastic paper. But trying to figure out how to accommodate masses as a part of generalizing this really led us in the right direction. And so you'll see in our paper, we discuss the metric. When we discuss the metric, we discuss the metric from geometry kinematics duality, and then we propose a different metric that we think maybe is more practically useful for theory, especially for theories with masses. So absolutely, that's a kind of a critical, it's not a detail. It's actually a critical component of the setup is that we can accommodate masses.
Thanks a lot.
Yeah, thanks for those questions.
Okay, any other question?
Oh, well, can I ask about soft theorem? How did you deal with soft theorem with this formalism?
Well, yeah. So the connection to the soft theorem is this geometric soft theorem. So if I take the theory with zero potential, then I can write these stripped amplitudes I, K, N as in the limit, this is just schematic, where I take N, the leg N to zero, okay, the momentum of the leg N, then this turns out to be equal to a covariant derivative in field space acting on the lower point stripped amplitude. So this is what those authors called the geometric soft theorem, okay? And so, but this has only been proven for field redefinitions without derivatives. So again, this is the covariant derivative in the standard picture of field space geometry. So the extension would be, how do you extend this theorem to functional geometry? And actually, we think we know how to do that, although it's not published. There's also, this is very interesting in and of itself. It's something I worked on to try to understand. This is for theories without a potential, it's probably true to all orders. For theories with a potential, it requires modifications even at tree level, but definitely, and also at one loop. So this is something I worked on with collaborators, and so we've investigated this. Now there's a sense of the one loop geometric soft theorems, and the kind of general statements we can make persist actually at one loop. We have to make modifications due to Eier divergences. So the key idea here is Eier divergences. but we were able to find divergences. We were able to find universal forms of the leading IR behavior. Yeah, so I think this is a very exciting, very nice way of understanding the ideas of soft theorems and amplitudes that has nothing to do with symmetries. And so it's a beautiful reframing of the subject, and we've made some progress even understanding it beyond tree level. So now the question that what I was talking about today opens up is how to see it, a version of this in functional geometry. And so we have some internal preliminary results where we think this holds, but this is still an open question. So that's what I was kind of alluding to.
Okay, so thank you for the nice talk, and hopefully all the questions were answered. And please feel free to send us a version of the notes. We will post it on our seminar library online.
Okay, perfect. Well, thank you very much for having me. It was a pleasure to talk to you, and I hope I see you in person sometime soon.
Sure. Okay, so let's move on to the last speaker of the day. Yes, do you hear me?
Yeah, I'm here.
Yes, so I need to ask your permission to record for our YouTube channel.
Yeah, please go ahead.
Yeah, just give me a moment. Yes, we can begin. Maybe can you share the screen?
Yeah.
Yes. So today's third speaker is Rodrigo Guaglia, and he's going to talk about post-inflationary enhancement of adiabatic perturbations.
Yes. So welcome everybody. First of all, thank you, Anish, for the nice invitation and for organizing this nice seminar series. As you mentioned, my name is Rodrigo. I am a fourth and last month's PhD candidate at the University of Groningen in the Netherlands in a dual program with the University of Mexico in Mexico. And today I will tell you about our most recent work in this business of multi-field inflation, where you can source the scalar perturbations from